Welcome to this video, and in this video we'll be looking at the synthesis of RC one-port networks. We look at one-port RC networks. For any transfer function to be implementable using the RC network, it must meet the following properties. So these are the properties of an implementable RC network. Number one, the poles and zeros lie on the negative real axis and alternate each other. So we have the poles and zeros. They lie on the negative real axis. And they interlace. All the poles and zeros of the transfer function must lie on the negative real axis and they interlace. Number two, the singularity that is nearest to the origin is a pole. So a pole is nearest to the origin. While a zero is nearest to infinity. Number three, the residues of the poles must be real and positive. The residues of the poles are real and positive. So these are the properties of an implementable transfer function using RC networks. The poles and zeros must lie on the negative real axis interlacing each other. Then a pole is nearest to the origin, while a zero is nearest to infinity. And then all the residues of the poles must be real and positive. Let's take an example of a transfer function and we test whether it meets the RC network properties. Suppose we have a transfer function z of s is equal to 3s squared plus 18s plus 24 divided by s squared plus 3s. Okay, so the poles and zeros must lie on the negative real axis. That is our first property. We need to determine the poles and zeros for our transfer function, which we can write as 3 into s squared plus 6s plus 8 divided by s into s plus 3, which you can also write as 3 into the factors for the numerator are 2 and 4, and therefore we can write this as s plus 2 into s plus 4 divided by s into s plus 3, from which we notice that then for the poles, we have a pole at s is equals to 0 and s is equals to -3. And for the zeros, we have the zeros at s is equals to -2 and s is equals to -4. If you sketch these poles and zeros on an S-plane, a plane of real to imaginary axis, we have this as 1, 2, 3, 4. This is 0. For the poles, we have a pole at 0 and a pole at -3. Then we have a 0 at -2 and a 0 at -4. So if we look at the position or the location of the poles, all the poles fall on the negative real axis, and we have a pole 0 arrangement. That means they interlace on the negative real axis, and property number 1 is realized. Property number 2 is that the singularity that is nearest to the origin is a pole. If you look at this, then we have a pole at the origin and a zero closer to negative infinity as opposed to the pole at -3 and the other zero at -2. And through that, then property number 2 is met because there is a pole at the origin and the last singularity is a zero, which is at -4. Next, we want to determine the residues of the poles. To determine the residues of the poles, we need to write the transfer function in partial fraction expansion, from which we determine the numerator terms. Our transfer function is of second order on both the numerator and denominator, and therefore to establish its partial fraction form, we need to perform the division as follows. So we can write this as 3s squared plus 18s plus 24. We divide these by s squared plus 3s, from which we get this to be 3 into 3s squared plus 9s, and the difference will be 9s plus 24. Our transfer function can now be written as 3 plus 9s plus 24 divided by s squared plus 3s, which we can write as 3 plus 9s plus 24 over s into s plus 3. So we need to put this into partial fraction form as follows. So 9s plus 24 over s into s plus 3 can be written as a over s plus b over s plus 3, where a is 9s plus 24 divided by s plus 3 when s is equals to 0, which we get this to be 8. Our b is 9s plus 24 divided by s when s is -3, which will give us -27 minus 24, which is -3, divided by -3, which is 1. You notice the numerator terms a and b are positive, and those are the residues of the poles, and therefore our property number 3 is met, from which our z of s can be written as 3 plus 8 over s plus 1 over s plus 3. And this is our transfer function in partial fraction form, and all the properties are met, and therefore it is implementable using RC networks. Next, we proceed to implement our transfer function using the 4 methods: the Foster series, Foster parallel, Kawawan, and Kawawan canonical forms. The first one is the Foster series. In the Foster series, as we saw in the LC networks, all the components are in series, and if there is any arrangement in parallel, it is in series with the entire network. So you can have a resistor, a capacitor, and if there is a resistor capacitor in parallel arrangement, then they are in series with the entire network. And this is the configuration of a Foster series RC network. For us to be able to implement in Foster series, we write the implementable transfer function in partial fraction form to establish the various components and their values. Our transfer function was given as z of s is 3s squared plus 18s plus 24 divided by s squared plus 3s, which we have tested. And in our process of testing, we wrote this in partial fraction form, as the same transfer function can be written in partial fraction form as 3 plus 8 over s plus 1 over s plus 3. So to proceed and write this as 3 plus 8 over s plus 1 over s plus 3. The first term is a constant. The first term is a constant, which indicates presence of a resistor whose resistance is the value of the constant, and therefore we have a resistor of 3 ohms. The second component is 8 over S, which we can write as 1 over 1 over 8S, which is similar to that is impedance due to a capacitor 1 over SC, and therefore that indicates the presence of a capacitor whose capacitance is 1 over 8 farad. Finally, we have the transfer function 1 over S plus 3, and that indicates we have a resistor and a capacitor in parallel. If you have a resistor and a capacitor in parallel as R and 1 over SC, the impedance is given by the impedance of an RC parallel combination will give us R multiplied by 1 over SC plus R over R plus 1 over SC, which we can write as R over SCR plus 1, which you can write as 1 over C over S plus 1 over RC. That means the numerator will be a constant, and the reciprocal of the constant will give us the value of the capacitor. So here we'll have a network that has a resistor in parallel with a capacitor, and the value of the capacitance will be obtained from the numerator term. And in this, if we compare our resistor capacitor parallel combination with 1 over S plus 3, we notice that 1 over C will be equal to 1, from which our capacitance will be 1 farad. Next, our 1 over RC, which is the constant in the denominator, will be compared to 3, from which we notice that then our R will be equal to 1 over 3C, which will be a third. And therefore, our resistor is 1 over 3 ohms. And this is the Foster series implementation of the transfer function using the RC network. Number 2, we look at the implementation using the Foster parallel, or the second Foster canonical form. In the Foster parallel network, we see that all the components are in parallel, and if there is any series arrangement, then the series arrangement is in parallel with the entire network. So we can have a network that has a resistor, a capacitor, and then a series resistor capacitor combination, but in parallel with the entire network. This is our arrangement, and that will be the implementation of the Foster parallel network. Now, for us to implement this, we need to write the transfer function as an admittance transfer function, because now the components constitute admittances. The admittance due to a resistor will be the reciprocal of the resistance. The admittance due to a capacitor is SC, and then the admittance due to a series capacitor resistor network is given by R plus 1 over SC, then the reciprocal. So our Z is R plus 1 over SC, which is SRC plus 1 over SC. That means the admittance will be SC over SRC plus 1, which we can write as S 1 over R over S plus 1 over RC. And as you notice, the numerator term will help us determine the resistance, and then from the denominator constant, we can determine the value of the capacitance, having established the value of the resistor. To implement the transfer function, then we are saying that we use the admittance transfer function, and we expand this in partial fraction expansion. If we take the admittance transfer function directly and expand it in partial fraction expansion, it results with partial fractions with negative residuals. And because we cannot have components with negative values, then we do not expand the admittance transfer function directly, but we first take the admittance transfer function, we divide it by S, and then we expand that in partial fraction form. Once we get the partial fraction form, and then we multiply by S, each of the terms by S, to get back our admittance transfer function in partial fraction form. And therefore, we will not expand the admittance transfer function directly, but rather we will first divide it by S, obtain the expansion in partial fraction form, and then proceed to multiply each of the components or each of the partial parts with S to get back our transfer function. Suppose we proceed to implement the same transfer function using the Foster parallel network. Our Z of S was given as 3S squared plus 18S plus 24 divided by S squared plus 3S. The admittance transfer function can be written as S squared plus 3S over 3S squared plus 18S plus 24, which we can write as a third into S plus 3 you can write into a third S into S plus 3 divided by S plus 2 into S plus 4. If we are to take the factors of the denominator, we factor out 3, which will give us a third, and then S plus 2 becomes the factors. Next, we proceed to write Y of S over S, which will be a third into S plus 3 over S plus 2 into S plus 4. We can write these in partial parts as Y of S over S will be a constant over S plus 3 plus a constant over S plus 4, from which then we can notice that our A will be equal to a third into S plus 3 over S plus 4 when S is equals to -2, which will give us a third into 1 and then divided by 2, which will be a sixth, and therefore A will be a sixth. Our B is a third into S plus 3 over S plus 2 when S is -4, which will give us a third into -1 divided by -2, and this will give us a 6. That means our Y of S over S will be 1 over 6 over S plus 3 plus 1 over 6 over S plus 4. Sorry, this is supposed to be S plus 2, and this is S plus 2. From these two factors, it's S plus 2. Next, we need to write our Y of S. We multiply both parts or each of the parts by S to get our terms as follows. Our Y of S now becomes a sixth S over S plus 2 plus a sixth S over S plus 4. If you look at those two parameters, they correspond to the admittance when you have a series connection of resistor capacitor, whose admittance is S into 1 over R divided by S plus 1 over RC. That means we can proceed and compare this with S of 1 over R, S plus 1 over RC. We compare this with 1 over 6S over S plus 2, from which we will notice that our R, 1 over R is 1 over 6. That means R is 6. R is 6 ohms. And then 1 over RC is 2. The constant is 2, from which C will be equal to 1 over 12 farads. In the next one, we compare 1 over 6S over S plus 4. We compare this with S 1 over R over L, S plus 1 over RC, from which again our R will be 6 ohms and our C will be equal to 1 over 4R, which is 1 over 24 farads. We can proceed now and draw our network as two sets of resistor capacitor series network, but then in parallel with each other. In the first one, our R is 6 ohms, and also in the second one, our R is 6 ohms. Our first capacitance is 1 over 12 farads, and our capacitance here is 1 over 24 farads. And this is the first parallel implementation of the transfer function using RC networks. Method number 3 is the Kawawan canonical form of the implementation of the transfer function. Look at the Kawawan RC network. In Kawawan RC network, we said that in Kawawan, we write the transfer function in descending powers of S and apply continuous fraction expansion. From the continuous fraction expansion, we get the components and their values based on the terms that we get out of the continuous fraction expansion. So we require to write the impedance transfer function in descending powers of S, and then we proceed to determine the component values. At the end of the day, the setup will involve a resistor in series, a capacitor in parallel, resistor in series, capacitor in parallel network, and this will constitute the Kawawan canonical form of the RC network. If we take our transfer function and implement it using Kawawan, our transfer function has been Z of S is 3S squared plus 18S plus 24. We divide this into S squared plus 3S. We proceed to write this in continuous fraction expansion as S squared plus 3S. We divide this into 3S squared plus 18S plus 24. To get 3S squared from S squared, I need 3. So multiply by 3 to get 3S squared plus 9S. And the difference will be 9S plus 24. Next, we divide these into S squared plus 3S, this term. I need S squared from 9S, and therefore I multiply this with 1 over 9S. 1 over 9S times 9S will give us S squared, which is S squared plus 24 over 9S, which is the same as 8 over 3S. And the difference is going to give us a third S. We divide the third S into the term here, which is 9S plus 24. I need 9S from 1 over 3S. I multiply this by 27 to get 9S. The remainder is 24, which I divide into a third S. To get a third S from 24, I need to multiply this by 1 over 72S. And the difference will be 0. And that is the end of our partial fraction expansion. From this, then we can draw the circuit as follows. The first component will indicate a resistor. So this is a resistor, and the resistance is going to be 3 ohms. The second term indicates admittance due to capacitor. Admittance due to capacitor is given by SC. If we compare this, then the capacitance is 1/9, and therefore this is 1/9 farads. Next, we have a resistor. The resistor, we compare 27 with the resistance, and therefore the resistance is 27 ohms. Finally, we have a capacitor or admittance due to capacitance. In that admittance, again, if you compare this with SC, it will be 1/72 farad. And this is the Kawawan implementation of the transfer function using RC networks. Finally, we can implement the transfer function using Kawawan canonical form of the RC network. In the Kawawan form, we write the transfer function in ascending powers of S and apply continuous fraction expansion. We write the transfer function in ascending powers of S and proceed to put it into continuous fraction expansion. Once we do that, then we obtain a network whose now terms are a capacitor in series and then a resistor in parallel arrangement. So capacitor, resistor, and so on. And this will be the nature or the configuration of our given RC network. If we implement the same transfer function, Z of S is 3S squared plus 18S plus 24 divided by S squared plus 3S plus S squared plus 3S. We can write this as in ascending powers of S as 24 plus 18S plus 3S squared divided by 3S plus S squared. So this is the transfer function in ascending powers of S on both the numerator and the denominator. We proceed to determine the continuous fraction expansion of the same transfer function, which will be 3S plus S squared So this is 3S plus S squared divided into 24 plus 18S plus 3S squared. We need 24 from 3S, and therefore we multiply this with 8 over S. So 8 over S times 3S will give us 24 plus 8S. And the difference is 10S plus 3S squared. Then we divide these into 3S plus S squared. We need 3S from 10S. That means we multiply this with 3 over 10. So if you multiply 3 over 10 by 10S, we get 3S. This is going to give us 3S plus 9 over 10S squared. And the difference is 1 over 10S squared, which again we divide into 10S plus 3S squared. To get 10S from 1 over 10S squared, then I need to divide these or to multiply this by 100 over S. You multiply 1 over 10S squared with 100 over S, we get 10S. The difference is 3S squared. And then we divide this into 1 over 10S squared. Then to get 1 over 10 from 3, we multiply it by 1 over 30. We multiply by 1 over 30, and that will give us 1 over 10S squared. The difference will be 0. So this is the continuous fraction expansion of our transfer function. Next, we can draw the circuit. We can draw the circuit as follows. So the first part, being a series part, indicates a capacitance in series which can be compared to 1 over SC, impedance due to capacitor, and from which we notice that our C will be 1 over 8. So we have a capacitor whose capacitance is 1 over 8 farad. Next, we have a resistor in parallel. So we compare this with admittance due to a resistor, which is 1 over R. And if 1 over R is 3 over 10, then R is 10 over 3 ohms. Next, we have a capacitor, 100 over S compared to 1 over SC. The value of the capacitance will be 1 over 100 farads. Finally, we have a resistor whose admittance is 1 over 30, or conductance is 1 over 30, and therefore the resistance will be 30 ohms. And this becomes the Kawawan implementation of the transfer function using RC network. And those are the 4 forms of implementation of RC networks: the Foster series, Foster parallel, Kawawan, and Kawawan. In all of them, we need to check for the properties of RC networks, and we said that the 3 properties are the poles and zeros all lie on the negative real axis and interlace. The pole is nearest to the origin and a zero is closest to infinity. And then number 3, all the residues of the poles must be real and positive. If those properties are met, any transfer function is implementable using one-port RC networks. Thank you for watching my video.